and all. This is Indrani of Institute of Aeronautical Engineering College. Today I want to deliver the lecture on the analog to digital converters. So this topic analog to digital converter will come under the subject name of the IC applications, or in few subjects of linear and digital IC applications. So in the data converters, this analog to digital converter, this topic will come. So first let us see what is the importance of the analog to digital converter. So here in the previous classes we have discussed regarding the digital to analog converter. So in the similar form, analog to digital converter means here there is a converter circuit will be there. So for the converter circuit we are giving the analog signal as the input and it is generating the binary code, right? Binary code. It may be a 3-bit, 4-bit or n number of bits is the binary code, that is the output signal it will generate. So here in this A2d converter, this is also called as the A2d converter. So this A2d converter basically it accepts analog input signal and produces the binary output word. So those binary output words I am representing as a B1, B2 and so on up to Bn, right? So otherwise we can represent that one as a D1, D2 and so on Dn. Whatever the form it is. Basically we are giving the analog input signal and it is generating the binary output signals, right? So the digital output D can be represented as B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus and so on Bn into 2 power minus n. So out of this, what is the B1 and Bn is, where B1 is the MSB bit and Bn is the LSB bit. So basically here the output is the digital output. The digital output is nothing but summation of, based on this expression, here B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus Bn and so on up to Bn into 2 power minus n. Suppose if it is a 3-bit. 3-bit means how it will come? For the 3-bit D equal to, it is represented as D equal to, capital D equal to B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus B3 into 2 power minus 3. If it is a 4-bit, then what will happen? In addition to this B3 into 2 power minus 3, the B4 into 2 power minus 4 is also will come into consideration, right? So based on the number of binary bits, the D expression can be written like this. Out of this, the B1 is the MSB bit and Bn, whatever this B4 is there, that is the LSB bit position. Now let us see what is the block diagram of that and what are the circuits which will realize this analog to digital converter. So this is the functional diagram of the analog to digital converter. If you observe, for this analog to digital converter, we are giving the input signal is the analog input signal and it is generating the binary output. Binary output says B1, B2 and so on up to Bn. And B1 is the MSB bit and Bn is the LSB bit. The combination of the total thing is the overall digital binary word. The binary word is represented as a D. Next, here if you observe here, there is a 2 more extra pins are there. That is a start and EOC. Start is nothing but start of conversion and EOC is the end of conversion. When this start of conversion can be used is when I am giving the analog input signal. Before giving the analog input signal, first while operating the analog to digital converter, first I will press the start signal and I will give the analog input signal for this ADC circuit, right? So once the digital conversion is over, at that time automatically the system will activate the EOC, end of conversion. So for this entire process, it will do the conversion process with respect to by taking the reference voltage into consideration, because here it is generating the analog signal is converting to binary form. The binary forms are ones and zeros. So with respect to considering the reference voltage V reference here, it is converting the analog signal into the binary word. So here the analog to digital converters are classified into two types. So whatever the conversion techniques are there, those are classified into two types here. First thing is the direct type ADC and another one is the integrating type of ADC. So let us see what is the direct type ADC and integrating type of ADC. So in this direct type of ADC, it will compare a given analog input signal with the internally generated equivalent signal. Means in this direct type of ADC, here we are giving the analog input signal for the circuit, right? So for the analog to digital converter, we are giving the input is the analog input signal. I am giving is the input, right? So for the ADC, I am giving the analog input signal. So here, whatever the internally generated signal is there, by comparing the analog input signal with the internally generated signal here, it will generate the output values as the binary bits in the form of ones and zeros it will generate. That is here with respect to internal signal, main thing we need to concentrate here is in the direct type ADC, by giving the analog input signal, it will compare the analog input signal with the internally generated signal. So with comparison, it will generate the corresponding binary bits at the output side. So here, the different types of the direct type of ADCs. First thing is the flash type comparator. Second thing is a counter type converter. Next one is a servo tracking converter and successive approximation type of converter. So today let us see each and every circuit diagram and let us go through all the direct type of ADCs. The contrast to this direct type of ADC, there is an integrating type of ADC. Basically, ADC is classified into two types. One is the direct type ADC and another one is the integrating type of ADC. Under the integrating type of ADC, what is meant by integrating type of ADC? In this integrating type of ADC, it will perform the conversion in an indirect manner. So that's why we are calling this one as a integrating type of ADC. Here, indirect manner means how it will do the conversion is first by changing the analog input signal to a linear function of time or frequency. First, whatever the analog input signal we are giving, first it will be converted in the form of a linear function with respect to time or frequency. Later, based on that, it will convert the remaining that linear function signal of time and frequency into the corresponding digital code type of word. So this is here, in this one, we are not comparing the analog signal with some other reference signal or internally generated signal. Here, simply, there is a conversion process of analog signal into the linear function of time or frequency conversion will be there. Later, we are converting into the digital code word. So, the two types, there is a two types of integrating type of converters. First thing is the charge balancing type of ADC and another one is the dual slope type of ADC. So in this session, let us see the direct type of ADC. So as I told you previously, the direct type of ADCs, we can realize the direct type of ADC by using the flash type converter, counter type converter, servo tracking converter and successive approximation type of converter. So first let us go for each and every circuit diagram. Yeah. So the first thing is a flash type of converter, or we can call this one as a comparator type of converter also. So here this flash type of converter, this is the simple type of A2d converter and it is at the same time it is a more fastest type of ADC and at the same time there is a more expensive type of ADC also. And the other name of this flash type of comparator is also called as a parallel comparator. Parallel comparator. So here this name has been given based on the circuit. While seeing the circuit, you can understand why we are calling this one as a why we are including the corresponding comparator word, and at the same time why we are calling this one as a parallel type of A2d converter or parallel type of comparator converter. So here this is also called as a parallel type of A2d converter. So this circuit is a simple circuit. Simply here we are using the so many types of comparator circuits, right? And each and every comparator, what is the function of a comparator? Suppose we have discussed about the comparator in the previous modules. In the comparator, what is the function of the comparator? This is the symbol for the comparator using the op-amp. So this is the positive terminal and this is the negative terminal, right? So here, if I give the input signal for this, and if I give the reference voltage as the another input for the negative terminal, the positive terminal voltage can be compared with respect to reference signal voltage, and after comparison it will generate the outputs in the form of the binary form, that is in the form of ones and zeros. It will generate the corresponding output value, right? So here see a comparator will simply do the comparison of the corresponding input signal with the reference voltage signal. After doing the comparison, it will if the input signal value is greater than the reference voltage signal value at the time, it will generate the output is logic 1. If the input signal is less than the reference voltage signal, it will generate the output is a logic 0, right? So here, and at the same time, in addition to the parallel comparator, so many comparator sessions we are taking. How many number of comparators we are taking is, suppose if it is a 3 bit. 3 bit means we are taking the 2 power 3 minus 1 number of the comparators. That is a totally 7 number of comparators based on the number of bits. Suppose if it is a n bit. For the n bit, we are taking the 2 power n minus 1 number of the comparators we are taking here. Next, here whatever the comparator outputs are there, we are giving the comparator outputs for the priority type of encoder, right? Priority encoder. So based on the priority encoder, based on the type of input we are giving for the priority encoder, it will generate the equivalent binary outputs. So this is the basic diagram of the flash type of comparator. See here, we are taking here is a 3-bit type of comparator. How? By seeing this circuit, how we can tell this is the 3-bit means. If we observe here, how many number of output bits I am getting? Here, finally, the output is 3-bit. So that's why I am calling this one as the 3-bit type of comparator, 3-bit type of flash comparator circuit, right? So here, if you see here for this 3-bit, as I told you previously, we are taking a series of parallel comparators. If you observe, all the comparators are connected in a parallel manner here, and at the same time, output of all the comparators are given as the input for the priority encoder. What is the type of priority encoder we are giving here is a 8-to-3 priority encoder. Here, as I told you, here we are taking this one is a 3-bit. 3-bit means 2 power 3 minus 1, that is a 7 number of comparators. We can take 7 number of comparators. But here we are taking 1, 2, 3, 4, 5, 6, 7 and 8. If you observe, for the 8 pin, actually there is no need of giving any comparator. So here totally you can, otherwise we can take this is the 8-bit comparator circuit. So here for the 3-bit I am taking the 8 number of the comparator circuits. So if you observe the comparator, what is the input I am giving for the comparator? So here the first comparator is given for 0 volts, and at the same time positive terminal of the comparator is given for simply all the positive terminals of the comparators has been given to, if you observe all the comparators, all the positive terminals of comparators has given for the analog input voltage of VA. If you see this connection of all the positive connection, all the positive connections are short circuited to the analog voltage VA. And what about the negative? Negative terminal of the comparator consists of the reference voltage, right? Reference voltage. So that's why here also the negative terminal is connected to the reference voltage here. Here the negative terminal is connected to 0 volts, directly it is short circuited to ground. Next, if you go for this negative terminal, this negative terminal is represented as a VR by 8. Why we are considering this one as a VR by 8 is, suppose if I see what is the voltage at this point. The voltage at this node is nothing but the supply voltage VR into this concerned resistance value from this node to the ground, that is a R divided by sum of all the resistances. Sum of all the resistances is R plus R plus R plus R plus and so on up to R, right? So here we are taking the and one more thing, this circuit should have one more resistance here. This is the R. So totally I am having the 8 resistances. So VR into R by 8 R, right? So that's why here it is represented as a R and R gets cancelled. So here the voltage at this node is represented as a VR by 8. Similarly, if I see what is the voltage at this node, the voltage at this node equal to VR into sum of the resistance from this node to the ground, that is a 2R by VR into 2R divided by 8R. Like that, here VR by 4 came into picture, and at the same time coming for this one, VR into 3R by 8R, VR into 4R by 8R, VR into 5R by 8R, right? VR into 6R by 8R. If you cancel, I can get 3 by 4 of VR. Next here, if I observe here, what is the voltage at this node is VR into 7R by 8R. So based on that, I am getting all the terms of the reference voltages I am getting by the potential divider network. For all the potential divider network, I am giving the supply voltage value is nothing but VR. The reference voltage is given as the input voltage for this potential divider network, right? So now, if you observe here, suppose I have given the analog input signal, right? The analog input signal, the voltage of the corresponding analog input signal is in between, just for understanding purpose I am telling here. Consider that the analog input voltage is in between 0 to 1 by 8 into VR. Okay. So here, if the analog input voltage, some analog input voltage I have given, the corresponding voltage is having the amplitude value is in between 0 to VR by 8. So if it is a 0 to VR by 8, now which comparator output is logic 1 and which comparator output is logic 0? If you see here, coming for this comparator of X1 comparator. So for this comparator, the negative potential value is nothing but 1 by 8 into VR. And the positive potential value is when the positive potential value is more than 1 by 8 into VR. At that time, the output of this comparator will go to logic 1. Right? So the negative reference voltage is VR by 8. And I have given the input signal in between 0 to 1 by 8 into VR. So for this comparator, I am giving, now if I see the voltage at this node and voltage at this node. Here the voltage at this node is less than 1 by 8 into VR and the voltage at this node is 1 by 8 into VR. So if this is the case, at that time what is the output of the X1 here? The output of X1 equal to simply 0. Why? Because the positive terminal voltage should be greater than this VR by 8. Then only I can get output of the comparator becomes logic 1. But I have given the input signal as in between 0 to VR by 8. So at that time, definitely the positive potential value is less than the negative potential value. At that time, I will get the output voltage value is logic 0. Right? Now, Coming for the down comparator. For this comparator, the voltage at this node is 0. And here through the voltage at this node is 0. Now, what is the voltage at this node? The voltage at this node is VA is less than VR by 8. Okay, this is the voltage at this node. It is less than VR by 8 I am having. So, this VR by 8, this positive potential value is more than the ground here. At that time, I will get the logic 1 as the output for the X0. Right? Logic 1 is the output for the X0. And here X1 value equal to 0. And what about the remaining one? Definitely these potential values for all these things is the positive potential is less than the concerned negative reference voltages values. So that's why obviously I will get the output voltage value for each and every comparator section is zeros. Right? At the time here I have given this outputs of the comparators are going as the input for the 8x3 priority encoder. When it is going as the input for the 8x3 priority encoder, so what is the purpose of the priority encoder? Priority encoder will give the first priority for the MSB bit. Okay, so whatever the MSB bit value is there, based on the MSB bit value, it will encode the MSB bit value and it will generate the corresponding equivalent binary output. Okay, so here suppose for example, if I take the 8x3 means it is having the 8 input bits and 3 output bits. That is a priority encoder I am talking here. Okay, so if I take the value says X0, X1, X2, X3. Otherwise, if I show the table here, right. So here, this is a tabular column for the priority encoder. So here, the first case I have discussed. For the first comparator, I am having the input voltage value, the analog input voltage value is between 0 to VR by 8. At that time, I got the output of the first comparator is X0 equal to 1 and remaining all the bits values are equal to 0. So here, the X0, it has here remaining all bits values are equal to 0 means it will encode this position and it will generate the output is 0, 0, 0. Right? So similarly, let us see the another example. So if I consider, now let us see the another example. Consider that the analog input voltage values in between 5 by 8 into VR and 3 by 4 into VR. Okay, I am taking the range as with respect to reference voltages. I am taking this range, right? So the analog input voltage value is between the 5 by 8 VR into VR and it is less than 3 by 4 into VR. That is the specific one. Now, if I give this one as the input for the analog input voltage, then which comparator outputs are 1 and which comparator outputs are 0. So, this is the 3 by 4th VR is coming as a, it is a less than 3 by 4th VR is coming as a input for the analog side, right? It is a less than the 3 by 4th VR. Here VA value is less than the 3 by 4th into VR. When VA value is less than 3 by 4th into VR, then what will happen? The potential value at this positive potential value is more. So I will get X0 value equal to 1. And what about this one? Yes, the VA value is more than VR by 8. I will get X1 value equal to 1. Again here, the VA value is more than 1 V by VR by 4. X1 value equal to 1. Now coming for this, here also I will get X3 value equal to 1. Next here also, the 3 by 4th of VR, the VA value is greater than the VR by 2. So that's why I will get the value equal to 1. Now coming for this one, the analog input voltage value VA is greater than 5 by 8 into VR. So I will get output value of this one equal to 1. And coming for this one here, the VA value is less than 3 by 4th VR. Here I have given the analog input voltage is less than 3 by 4th VR. Then, but the reference voltage value is 3 by 4th into VR. At the time, what is the output I will get? The output I will get here is a logic 0. Similarly, here also logic 0 is the output I will get, because here negative potential, negative reference voltage became more than the analog input signal voltage. So that's why I got the output of those comparators are zeros. Now, based on these inputs, this is the priority encoder. Priority encoder will give the highest priority for the MSB bit value which is having the equivalent value equal to 1, right? So here this is the LSB bit and this is the MSB bit here. Out of all these sessions here, which is having which MSB bit value is 1? This MSB bit value is 1. So here the equivalent value of the encoded value of X5 will be present at the output side. What is the encoded value of the X5? This value is 101. 101, right? So I think it's clear. So now if I show the table here, now this is the truth table format of the flash type comparator. If you see here, X1 value equal to 1, it ignore whatever may be the value of the lower significant bit value, it will give the priority for the MSB bit. So here X1 value equal to 1, it has generated 1. X2 value equal to 1 mainly, so that's why it has generated 0, 1, 0. Here X3 value equal to 1, 3, 4, 5, 6, 7. Yeah. So here this is the priority encoder. Whatever may be the values under the lower significant bits, yeah, below bits, you don't consider whether the value is 0 or 1, only MSB bit value can be converted, right? So next, what are the advantages of the flash type comparator? So here this flash type of comparator is it is a simple, the operation wise is very simple. Simply we are having the comparator and the corresponding priority encoder section itself, right? So, and it is a most efficient and speed of operation is also more. Parallelly at a time it is comparing all the outputs of the comparator and immediately I will get the output value as a digital output value I will get it. So this is a very fast, and here what is a it is a limited only in terms of the comparator and the gate propagation delay. Means here the propagation delay is less itself. At a time we are giving the analog input signal, at a time within a fraction of seconds it will generate the output signal. Yeah, there is a delay is less with respect to this. But what is the drawbacks with respect to this? What is the drawbacks is it is a lower resolution and it is very expensive. Why? Because how many number of bits are required, that much number of comparators I need to take. Suppose if you see the previous one, for the 3 bit I have taken the 8 comparators. If it is a 5 bit means I need to take the 32 bit comparator I need to take. 32 comparators. 32 comparators I need to take, and at the same time 32 by 5 priority encoder I need to take. So as the number of bits are increasing, the circuit complexity is increasing. So obviously it is a more expensive. And at the same time, suppose if it is a 8 bit, I need to take 256 of comparators I need to take. This is a drawback. Circuit complexity is more, cost is also more, right? Due to this, obviously, we will get a lot of power dissipation with respect to the entire model. So that's why we are going for the another type of section is the counter type of ADC. Counter type of ADC. So in this counter type of ADC, here this counter type of ADC is the inverse of the D to A converter. So in the previous session we have seen the D to A conversion. So it is a reverse form of the D to A conversion is the counter type of the ADC circuit. So in this one, the first thing is we need to adjust the corresponding input code word for the DAC. Means if I show the circuit, you can understand what's that. Yeah. So here this is the DAC. Okay, so basically the first thing is the counter type of ADC block having the one comparator type of circuit is there, and here D to A converter. D to A converter which will convert the digital input to the equivalent analog output form. Digital input can be converted into equivalent analog output form, it will convert, right? So here now and for the comparator, the corresponding Analog output I am giving as the input for the comparator. Whatever the analog input signal is there for the comparator, one of the input of the comparator is the analog input signal, and another input for the comparator is the corresponding output of the D2A converter. Output of the D2A converter. Next, this comparator will compare the analog input signal with the D2A converter output, and it will generate the comparator output value is either the logic 1 or logic 0. Suppose if the VA value is greater than VD, I will get the comparator output is logic 1. If the VA is less than VD, I will get the output value is logic 0. Right? So here definitely if I give the analog input signal for this comparator, definitely I will get the corresponding output value equal to 1. And if you observe this circuit, so here and at the same time the output of this comparator I am giving as the input for the AND gate. For this AND gate, the input, another input of the AND gate is clock has been given. The output of this AND gate is given as the input for the binary counter. For this binary counter, the binary counter is, it will count the binary numbers, right? Binary number count will be done. Okay, so here for this binary counter, we are giving the reset type of input we are giving, right? So if you observe the output of this binary counter, this is the LSB bit and this is the MSB bit position. So it will generating the digital output. So the digital output I am giving as the input for the DAC circuit. So this DAC circuit will generate equivalent analog signal output, equivalent analog output for the digital input value. Okay, now before starting the circuit, suppose here I have given the analog input signal. So before starting the operation, what we need to do, the first step here is, first I need to set the DAC output value. How to set the DAC output value is, to what value I need to set the DAC output is, I need to set the DAC output in between plus or minus of half LSB. Okay, plus or minus of half LSB means here to get the plus or minus half LSB, I need to give that much amount of the digital input word I need to give as the input for this DAC circuit. Okay, so the first step in this process is, first before giving the analog input signal here, first I need to set the DAC output such that the DAC output should generate, the output DAC should be in the range of plus or minus half LSB. To generate plus or minus half LSB as the output, that equivalent digital input code word externally, by giving some another type of external circuit, I need to set some digital input for the DAC circuit, okay, which will generate the output value as between plus or minus half LSB. Okay, so after setting that, now I will give the analog input signal for the circuit. After giving this analog input signal, the output of this DAC is set to plus or minus half LSB. Now I have given the analog input signal. So your comparator will compare the analog input signal value with the digital, the DAC output value. If the VA value is definitely it is greater than VD, then output of this comparator is 1 here. When the output of this comparator is 1, and this output is going as the input for the AND gate here. For this AND gate, we are giving the clock pulses. So when the output of comparator is 1, then only your clock will go as the input for the AND gate. Continuously clock will go as the input for the AND gate. But the output of AND gate is 1 when the comparator output value equal to 1. When the output of this AND gate is 1, when this output of this AND gate is 1, when the clock is high, and at the same time mainly when the comparator output is high, then only I can get the output of AND gate is 1 I will get here. Okay, once it is 1, at that time your binary counter starts counting the value. Okay, so in what way it will count? So at one time it got the clock, it identified that the clock one clock has been passed. One clock has been passed means indirectly it is a comparator output value is 1. That is the meaning of that. When the comparator output value is 1, then only I will get the output of this AND gate is also 1. I will get it. Okay, output of AND gate is also 1. I will get it. So when the output is 1 here, your binary counter will count the corresponding clock as 1. One clock pulse has been counted. Like that it will consider. So after counting the clock, so whatever the clock is there, this clock will go as the LSB bit and remaining all the bits are equal to zeros. Okay, again, later, again here, for this equivalent digital input, again your DAC converter will convert the digital input into equivalent analog output. So for this analog, for the 0001, it is generating some certain amount of voltage at the output of the DAC. Again, there is a comparison of analog input signal to the DAC output, and again it will generate the output value. Definitely I will get VA value is greater than VD and comparator output value equal to 1, and again your AND gate output value equal to 1. Your binary counter starts a count. It will take the next clock. It will count to the previous values. 1 is the clock it got. Now it got the second clock can be counted. Like this process continuously gets repeated. Here comparison, AND gate output as a clock, and your binary counter starts counting the corresponding number of clock pulses. Okay, so when this process gets completed, is here whenever I'm getting continuously the VA value is less than VD. Whenever the VA value is continuously less than VD, at the time the comparator output value is 0. When the comparator output value equal to 0, AND gate output value is also 0. AND gate output value equal to 0 means your binary counter stops counting the value. Right? Your binary counter stops the counting the value. Okay. If this is a continuously going on at the time, automatically your circuit will identify that yes, conversion process is over. Okay, conversion process is over. Automatically, whatever the binary, the digital output I got till that time, that is a digital output for equivalent analog input signal. Okay, so suppose if it is after 10 clock cycles, continuously the corresponding output of AND gate is 0. Okay, so at the time the output of the binary counter is stuck to 0101. If it is a 4-bit 01, consider that the clock pulse counted by the counter is 10 clock pulses has been counted, means 1010. Okay, so this 1010 is the equivalent binary value for this analog input signal. This 1010 is the equivalent binary value for this analog input signal. Right? So here, if you see for this conversion process, whatever the analog input signal is there, every time it will do the binary counter will start the counting from 0 to, suppose if it is a n bit. N bit means the analog input signal is having the equivalent digital value is n bit. At that time, it will do the counting for 2 power n minus 1 times. Means here your binary counter will count the number of clock pulses it will count is 2 power n minus 1 number of clock pulses it will count here. After 2 power n minus 1 number of clock pulses, it will generate the exact digital output value. Okay, exact digital output value. Whatever the digital output value I am getting here, that is the equivalent digital output value for this analog input signal. Okay, that is the meaning of that. Okay, here whatever this staircase waveform is there, this is a staircase waveform for the DAC output. Here this DAC output always it will generate the staircase waveform. What is a staircase waveform is for if all the values are zeros, it is having certain voltage value. That is previously we have seen. It is less than VR by 8 like that. if it is a 001, then I will get the voltage value is greater than VR by 8. Greater than VR by 8, I will get the voltage value. If it is a 010, I will get some other voltage value. For each and every binary bit, I will get a different output analog voltage for the DAC, right? So that's why it is represented like this. It is represented like this. So here output of the DAC is like a staircase. I will get the corresponding output value. Staircase output value I will get, and these are the clock pulses. Just assume that the number of clock pulses counted with the counter is 8 clock pulses has been counted, and for 8 clock pulses the DAC output I am getting is a staircase type of output like this I am getting here, right? So here what are the reset and reset is there. Here when the reset pin is came to low, then only your binary counter is on, and at the time it is counting the number of clock pulses. Basically, if it is counted, the number of clock pulses 8 clock pulses has been counted. When the 8 clock pulses has been counted here, the counting will stop. Okay, counting will stop, and it will generate the binary word is nothing but 1000. Okay, so after that again your counting stops, and after certain duration your if you want to again give the analog input signal, now again I need to do the switch on the reset button for the binary counter. Reset button for the binary counter. If you want to give further analog signal, I need to give again the reset signal, and the new analog input signal I can give as the input for the counter type of ADC. So here whatever the thing I have explained here, same thing has been given. This is about the comparator, and when VA value is greater than VD, the output of comparator become high, and the gate is allowed to transmit the clock pulses. Yeah. So same thing, whatever we have discussed now, same thing has been given. Here basically, whatever the counter frequency is there, the counter frequency should be low enough and enough to give the sufficient time for the DAC to settle and the comparator to respond low. This is the main drawback with respect to the circuit, because here the operation wise, based on the analog signal, slowly it is doing the entire process of the comparison DAC output. Yeah, so DAC, if suppose if the DAC is not working fastly at the time, comparison also becomes slow. Comparison becomes slow means I can get the output of the AND gate is also slow, and your binary counter also slowly it will do the process of counting. So entire process, the speed of operation is very less. This is the main drawback with respect to this counter type of ADC. Okay, and at the same time, as I told you previously, the conversion time for the clock analog input voltage is 2 power n minus 1 clock periods are required. 2 power n minus 1 clock periods are required. So after 2 power n minus 1 clock pulses only, for complete clock pulses only, then only it will finalize what is the output value. Okay, what is the output value, right? So suppose if it is a 12 bit and I'm having the clock frequencies, the frequency of the clock pulse is 1 megahertz. At the time the counter will take 2 power n 1 minus 1 microseconds. If I convert this frequency into time period, I will get 4.095 milliseconds to convert the analog input signal to the corresponding digital output signal. This is the it is taking lot of time. Lot of time it is taking means the speed of operation is less with respect to this circuit. So here, what are the advantages and disadvantages of this one? The counter type of ADC, it is having the simple components, right? So it is very easy to operate, and at the same time it is a less complex, and it is the cost is also very less. And coming for the disadvantage, the speed is less. Okay, so here always your counter will start from 0. Yeah. So next here for the completion of one process and for giving the next process, it will take a lot of time. It is taking for completion of this process. Entirely the speed and delay is more with respect to this counter type of ADC. Next one is a servo tracking type of ADC. What is the servo tracking type of ADCs? If you see here, what is the difference between the previous model and the present model here? In the previous model, we have taken one AND gate we have taken. That AND gate is removed here. Next, analog input, same. Comparator, DAC, both components are same here. These two components are same. And next here, in the place of binary counter, I am using the up-down counter I am using here. Okay, up-down counter I am using here. So now, here, if you observe, let us see what is the operation. So, in the servo tracking type of ADC, in the servo tracking type of ADC here, these so servo tracking type of converter, here always your DAC circuit will track the corresponding analog input signal value. Based on the analog input signal value, either the comparator output value is 1 or 0. Suppose if the VA value is greater than VD, VD is nothing but output of the D to A converter, output of the D to A converter. So here, when the VA value is greater than VD here, I will get output is logic 1. Output is logic 1. When the output is logic 1, this output of this comparator will going as the input for the up-down counter, and this output of this comparator is called as a control input for the up-down counter. Okay, control input for the up-down counter. So, when the control input value equal to 1, here directly we are giving the clock pulse. We are giving the clock pulse. When the control input value equal to 1, your up-down counter, if the control input value equal to 1, then the up-down counter will count the up operation. When the control input value equal to 1, it will count the corresponding up-down counter will act as a binary up counter. Means the corresponding binary value will be increased by 1 bit. Right? So, when this condition will get, we will get this condition when VA value is greater than VD, I will get the up-down counter will do the operation say up counting, and for doing the operation of up counting here, the VA value should be greater than VD and your comparator output value should be 1. When the comparator output value is 1, control value equal to 1. When the control input value equal to 1, your counter will do the up operation. Okay, so similarly, if I see the second thing, when the VA value is less than VD, when VA value is less than VD, what will happen? The comparator output value equal to 0. When the comparator output value equal to 0, the control input, the comparator output is nothing but control pin. The control value equal to 0. This control 0 will going as the input for the up-down counter. When the up-down counter is getting the control input value equal to 0, it will do the down counting. Down counting. Here if you observe, when the control value equal to 1, up operation is going on. When the control value equal to 0, down counting operation is going on. Like that, here it will do the comparison of the corresponding analog signal will be completely compared with respect to the digital output. So based on the comparison, comparator output value is either 1 or 0 here. So when the control output value is 1, then your up down counter will do when the control input value equal to 1, it will do the up operation. When the control value equal to 0, it will do the down operation, right? So, after completion of entire thing, when the VA value becoming continuously equal to VD, okay, when VA value is continuously becoming VD, then what will happen? The counter will understand that yes, total conversion operation is over. Okay, so automatically the entire circuit will stop and the equivalent digital output I will get here is the up-down counter output is nothing but equivalent digital output for this analog input signal. Okay, for this analog input signal, right? So here up-down counter is having the MSB bit value is this one and this is the LSB position. Yeah, so I think it's clear. So if you see the graph here, here in this graph, this is the analog input signal. This is the analog input signal. Next, what are the staircases there? The D to A converter will generate the output value is a staircase type of output. Yeah, staircase type of output. This staircase type of output will go as the input for this comparator. and this analog input is also going as the input for the comparator. Now, if you observe here, for the entire duration of the time, the VA value is greater than the VD value. Yeah, entire duration of the time, VA value is greater than VD. Now your control value equal to 1. So your up-down counter is having the input of this, whatever this waveform is there, this waveform is nothing but input of the up-down counter. Input of the up-down counter is equal to continuously 1 up to here. Again, if you observe here, in this one, the VD value is greater than VA. VD value is greater than VA means here, after comparison, the control output value equal to 0. So that's why here I am getting the 0. So here, this is the binary counter will do the up counting, and here the binary counter will do the down counting operation. Yeah, like this, whatever this waveform it is showing here, it is continuously shows like this, right? So this is the description for this model, right? Here also we are setting the DAC to the initially plus or minus 1 LSB value. First we need to initiate the DAC circuit. For the previous model we have set it that one to plus or minus half LSB, right? So here in the servo tracking type of ADC here, the analog, as long as the analog input changes slowly, then the track ADC will be within the 1 LSB of the correct value itself. Okay, so here also while doing the conversion process here also while doing the conversion process, it will take a lot of time to do the conversion, but the design is simple. Okay, and shift registers are not needed for this one, and at the same time the corresponding here, yeah. So but compared to the previous model of the counter type of ADC, the speed is high for this one, right? And at the same time, yeah. So next thing is the up-down counter is a little bit complex compared to the previous model. And here, and the whatever the conversion time is there, the conversion time is proportional to the analog input signal rate. Suppose if the analog input signal is coming very slowly, then the time taken to convert the analog to digital also process will done very slowly. Okay, suppose if the analog to digital conversion is process is very fast, at that time I will get the digital output also, I will get the faster digital output, I will get it. Last type of the converter is the successive approximation converter. This is a very successful model. Why? Because here for the previous models of the counter type of ADC and servo tracking type of ADC, for the n-bit conversion it is taking the 2 power n minus 1 clock pulses. It is taking 2 power n minus 1 clock pulses means it is taking the lot of time. That is the drawback with respect to the previous type of analog to digital converters. But for this one, if it is a n-bit conversion, just it will take the n clock periods it will take. If it is a 8-bit conversion, simply it will take the 8 clock pulses to convert the 8-bit conversion process, right? So let us see the operation. So for this one, we are using the some successive approximation register we are using. For the previous models, we are not using any of the registers. We are using simply the counters of binary counter or up-down counter we are using, right? So here entire process will be done based on the trial and error method itself. Completely it is based on the trial and error method itself. Now if you see here, just observe this model. Here one thing, here this is the positive of the comparator and this is the negative of the comparator, right? Okay. So now if you observe this successive approximation type of converter. In this successive approximation type of converter, we are taking the successive approximation register, right? So for this successive approximation register, we are giving the clock inputs as the inputs, and for this one here SOC and EOC is there. That is a start of conversion, end of conversion. Okay, start of conversion means while I am giving the analog input signal, before giving the analog input signal, I will switch on the start of conversion, right? So once the process of converting the analog to the corresponding digital conversion is over, when the process of analog to digital conversion is over, then automatically your circuit will activate the end of conversion. End of conversion. Okay. So now while seeing the logic here. So in this one, same thing, your DAC will be set it to plus or minus 1 LSB position, right? So I have given the analog input signal. First thing is when I'm starting the SOC, immediately the successive approximation register will make outputs as 1000. Okay. Once if I start the SOC, the first step it will take is, it will set the MSB bit position value equal to 1, remaining all the bits values are equal to 0. For this value of this digital input, this DAC circuit will convert this digital input into equivalent analog output. Now, this analog output is giving as an input for the comparator. Another type of input we are giving for the comparator is analog input we are giving, and this analog DAC output is another input going as an input for the comparator. Now, when the VA value is greater than VD, if this condition satisfies, then your successive approximation register will make the MSB bit value is kept as it is 1. Okay. When this condition of VA greater than VD condition satisfies, then the next MSB bit, next highest LSB bit value is made as 1. Remaining all bits are equal to zeros. When this thing will come, when VA greater than VD, this MSB bit value is kept as it is as 1, and next highest LSB bit is given as a activated to 1. Okay. Now this time your DAC will get the input of this DAC is 110. For this equivalent value, again it will convert this digital input value to equivalent analog output. Okay. So again your analog signal will be compared with respect to the VD, and after comparison, suppose consider that I got the VA value is less than the VD. I got. When the VA value is less than VD, what it will do? The successive approximation register will make this one is 1, and previously it kept this one is 1 here. So it will change this 1 position to 0 and makes the next lower LSB bit to 1 and kept the remaining bits all are equal to 0. Okay. Understand this logic. When the VA value is less than VD, okay, comparator output value equal to 0. When the comparator output value equal to 0, your successive approximation register will make the previous 1 is changed to 0. Previous MSB bit 1 has been changed to 0. Next LSB bit value can be changed from 0 to 1. Now your DAC circuit will have the present output of the present input for the DAC is 1010 like this, right? Again it is generating the digital, and again comparison. So based on the comparison, if the value equal to 1, the concerned bit value is made as 1, and next LSB bit value is made as a 1. Yeah, like this entire process will be done for this one. Completely this is the trial and error process. Right? So if I show the whatever I have described, the same thing has been mentioned here also. Okay. So initially the SAR will make the DAC, SAR will generate when the SO start command came into picture, then SAR will generate the output values 10000. Okay. For this one, the DAC will set the equivalent. The digital input can be converted into analog output. The analog output we are giving as an input for the comparator. Another input for the comparator is analog input VA. Yeah, VA is compared with VD, and the successive approximation register will make the trial and error process. For example, just imagine that. Here, the correct digital representation here is 11010100. Yeah, I'm having the my analog signal. My analog signal is having the equivalent digital output is like this. I'm having 11010100. This is the exact one. Okay, so let us see. First, I have started the start of conversion. I have started. Click the start of conversion command. Then immediately the SAR register will generate the output value equal to 10000 like this. At the time, the comparator output value is initially 1. Right. Here, there is a comparison of the analog input signal with this value. Definitely the comparator output value is 1. When the comparator output value equal to 1, again, this same MSB bit is kept as it is 1. The next highest LSB bit value is taken as a 0 to 1. Okay. So again, this one I am giving as an input for the DAC. Okay, input for the DAC. I got the output of the comparator is 1 I got. When the output of comparator is 1, again your successive approximation register will make this MSB as is, and next LSB bit value is changed from 0 to 1 like this. Once it is changed from 0 to 1, right? So here if you see here, my required digital one is like this and this is the obtained one. Now if you observe VD value here, the corresponding this one will go again as an input for the DAC circuit. Yeah, definitely your DAC will generate the equivalent analog values greater than this VA value, right? This VD value become greater than VA, and at the time I will get the comparator output value equal to 0. When the comparator output value equal to 0, again there is a 1 to 0 transition, and the next LSB bit is changed from 0 to 1 like this. So if you observe entire process, you can understand this one. Yeah, 0, 1. Again, I got the corresponding VD values less than VA. So I got the comparator output value equal to 1. Again, your SCR make the MSB bit value as it is. 0 can be changed to 1 like this. So if you see here, for this, for example, if you see this for this 8 bit, I need the for the VA, I need to get the VA for the equivalent output of the VA is 8 bit. For the 8 bit, how many clock cycles it has taken? It has taken the number of clock cycles is 1, 2, 3, 4, 5, 6, 7, 8. Within 8 clock cycles, I got the what is the exact output value. If you observe this all the exact output values here, this one, and this overall output of the comparator, all are equal. How many cycles it has taken? Totally 8 clock cycles has been taken. Suppose if I take the previous counter type of ADC and the servo tracking ADC, it will take the number of conversion time here is there it will take 2 power 8 minus 1 number of clock cycles are required for the previous operations. But here within the 8 clock cycles I have completed the entire process. Yeah, speed of operation is more and here the delay is very less, right? So this is the about the successive approximation type of converter. So what are the advantages and disadvantages? The speed is high compared to previous one. Yeah, good speed to power ratio, right? And it is inexpensive and it uses only one comparator and there's a low power consumption. And what is the drawback? Drawback here is cost is high because of why the cost is high is the successive approximation register it is costly, right? And it's a complexity in the design. But remaining advantage is the delay is less and the speed of operation is more with respect to this circuit. Okay, so I think it's clear away. These are the all the 4 types of nothing but the direct type of analog to digital converters. In the next coming session, let us see the other type of indirect type of ADCs. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.